So we get very different answers to what we expect to see for the expectation value of the density operator, depending whether our system starts in a coherent state or Fock state. Let's have a look at the coherent state. Now we've fortunately already arranged all of these products to be in normal order, so all we have to do is we apply all the annihilation operators forwards, and we apply all the creation operators backwards, and when we apply this forwards, because the coherent state is an eigenstate of the annihilation operator, we'll just get that coherent state value coming out, and when we apply it backwards, we just get the complex conjugate of it, because it's the same thing as applying the annihilation operator forwards. And so what we see there is we're going to get beautiful interference fringes. If we have coherent states alpha 1 and alpha 2 for our two modes, then when they interfere, we're going to see a beautiful set of interference fringes that depend on the position x. Now what do we get if we start off in number states? Well, these are just the number operators precisely, so those terms are easy. And these two terms are easy for a different reason. If the second annihilation operator acts forwards, it's going to drop the second number by 1. And if the first creation operator acts backwards, it's going to drop the first number by 1, which means this term is going to have n1 minus 1 and n2 on one side, some factors, and n1, n2 minus 1. And the simple fact is that those two number states are different number states, strictly different number states, so that inner product is definitely 0. So in fact, this is the answer. What we're going to get when we measure the average density if the two condensates are in number states is we're going to get a completely even average. So there's going to be no spatial dependence at all. We don't expect to see interference fringes. So what do you actually get when you take two condensates and you drop them on top of each other? It turns out you get interference fringes. And this was shown by Wolflane-Kedley's group at MIT in 1995. And so one might be forgiven for inferring that therefore they're more likely to be in coherent states than number states. In fact, this is a very early interference experiment. After some time, people got very good at making these interference experiments. This process is actually the method by which the most sensitive inertial measurements are made these days. Here's Kyle Hardman posing with the ANU prototype of an inertial sensor. What it does is it takes a Bose-Einstein condensate, breaks it into two pieces, drops it down, and the two pieces travel through different paths. When they recombine, the difference in the gravitational field, the different paths experienced over that travel time, gives them a particular interference pattern. That interference pattern therefore tells us about the gravity. And when you measure gravity sensitively enough, you find that it actually changes in time. So not only does the water on the Earth move according to the tides, but so does the actual solid Earth as well. And here you see a picture of the solid Earth tide actually measurably changing the gravity in the laboratory over a period of a day and a half. And so we see not only is interference of two condensates giving us interference fringes, it's giving us interference fringes that we can control so well that we can use them to make precise measurements.